All right, we're going to get started now. So last time we were left off talking about the measurement lab, and we collected the data for the indirect determination of the mass and volume of one drop of water, but we didn't do the calculations. So let's go ahead and do the calculations. See, it's nice to be able to do the calculations while in lab, because if we get some ridiculous number that's not within the range that we expect, then we can recollect the data just to check. Or if our percentage error comes out big, like for example, on the density of copper, I would have preferred to redo that because the percentage error was around 2%. I'd like the percentage error less than 1%. And so I would redo that if there's time. But if there's no time, then we just got to go with the data that we have. And here, let's take a look at the calculations for this. So we collected the mass of graduate, the drops of water added, the mass of the graduate in water, and the volume of the water. And so we can calculate the mass of the water. The mass of the water is we just take the mass of the graduated cylinder plus water minus the mass of the graduated cylinder. And so let's go ahead and get the mass of the water. And so here I have the 40.51 for the mass of the graduated cylinder plus water minus 3746 for the mass of the graduated cylinder without water. And so that gives me 3.05 grams. And so we can put that in here, the mass of H2O, which is our calculated value here, is 3.05 grams. All right, what's the next calculation that we do here? The next calculation is the mass of one drop of water. Okay, this is the mass of 60 drops of water. And so to get the mass of one drop of water, we could do that calculation here. The mass of one drop of H2O is going to be 3.05 grams per 60 drops. And so we'll just do it, divide 3.05 by 60. So divided by 60 equals 0.05083. And so 0.05083 grams per one drop. How many sig figs are we allowed? Well, 60 will take as exact, so we're allowed 3 sig figs. And so this is going to give us 0.0508 grams per drop. Or just, we could also just say grams because it's already associated with one drop here. Okay, what's the next calculation here? The next calculation is we're going to do this. Okay, we have oops, I didn't want to write it there. You know, we want to keep the report sheet clean. We should do this in our notebook. And so they want us to do a dimensional analysis calculation here. And so that's what all this business is about. And so I'm going to do that up here. And so we're going to just take 0.05, I'll just go with 3 sig figs here, 508 grams per drop. And then they want us to convert it into micrograms per drop. I would rather do milligrams. This would be 50 milligrams, 50.8 milligrams. But if we do micrograms per drop, then we know that there are 1 million, or 1 times 10 to the 6 micrograms in a gram. And so 1 million micrograms in a gram. And so we just move the decimals 6 places over. So that's one way of doing it, or just multiply it. I'll just multiply it. And so I'm going to just do times 1 times 10 to the 6th. That equals 50,833 micrograms. And so what is this equal to? This is equal to 50,008. Well, I'm only doing 3 sig figs. And so I'll do 50,800, micrograms per drop. or better to do this milligrams, 50.8 milligrams of water per drop of water. I would have preferred that, but either of these are okay. It's just easier. Now, the last calculation here is volume of 1 drop of water. And so we have the mass of 1 drop of water. Now we're going to do the volume. So we got the mass in grams per drop. Oops. We got the mass in micrograms per drop. We have the mass in milligrams per drop. Okay, so the volume of 1 drop of water in milliliters. So we have the volume of 60 drops of water here. And so I ran out of room here. I'm going to do that up here. So this is mass calculation. Now we're going to do our volume calculation here. Oops. Volume calculation here. And so we have 3.02 milliliters for 60 drops. And so how many milliliters is just 1 drop? And so let's calculate it. So we're just going to take 3.02 divided by 60. 2 divided by 60. That's going to give us 0.053. 503. And what we're going to do is we're just going to do 3 sig figs. This would be a 3 here, milliliters, and then we can round it to 0.0503 milliliters per 1 drop. Okay. We could also do this dimensional analysis too, but we'll do it this way here. So that's how many milliliters we have in 1 drop to 3 sig figs. All right, now they want us to do some unit conversions here. So we're going to go from milliliters per drop to microliters per drop. And so we need to do a milliliter to microliter conversion. They're kind of mapping it out for us, but we could figure this out just using dimensional analysis. And so just carrying this on, I'll do that calculation here. So if we take this answer and then multiply it by, well, what we're going to do is we're going to convert milliliters into liters. It's probably best. And so 1 liter is 1,000 milliliters. And so the milliliters will cancel, leaving us with liters. And then we're going to microliters. And so there are 1 million, 1 times 10 to the 6 microliters per liter. And so I'll just take the previous answer here and then divide it by 1,000. Okay. Times a million. 1 times 10 to the 6 equals 50.3. So this comes out to 50.3. In other words, to go from milliliters to microliters, we got to move the decimal 3 more over, because milli is 1,000. Excuse me, milli is 1,000. Micro is a million. So the difference between 1,000 and a million is 10 to the 3rd. And so 50.3 microliters per drop. And so here, microliters per drop is probably best unit to use in this case, 50.3 microliters in 1 drop of water. All right, so that's this calculation along the bottom of the report sheet here. All right, we skipped C and didn't quite, we started C, but we didn't quite finish it. So we had the color of the packet, and so just refreshing, as it was last week, refresh where we were. The color packet was green. And then we measured the mass of the packet with a triple beam balance. With a triple beam balance, we put 1,000 grams, 100 grams, 30 grams, and 2.55 grams to give us a total mass of 1,137.55 grams for that. Okay, the way the triple beam balance works is we're taking that as exactly 1,000, exactly 100, exactly 30, and the uncertainty is going to be in this last. So this is measuring to the nearest, tenth, a hundredth of a gram. A hundredth of a gram is also called a centigram, so we're measuring to the nearest centigram in this case. A thousandth of a gram is a milligram, so if we went one more place over, it would be a milligram. A milligram would be a little higher precision. Now, you know, it depends on these masses here. You know, what is the uncertainty in those masses? And so we don't know, but I don't think they're exact. We're going to take them as exact, just for purposes. I mean, if we can't take 1,000 exact, then the uncertainty is going to be huge. All right, so we have the color of the packet, and then we have the mass, and so 1,137. Now we need the mass of the plastic cover. We aren't going to measure that. The mass of the plastic cover is given on the packet itself. So this is going to be the tare weight. So somebody had already weighed the plastic cover. Tare is kind of your zero weight, so we have to subtract that. The plastic, total amount of plastic and these labels that they use is 21.98 grams. And so we'll just write that here. And so this is the mass of the packet. This is what you write in your notebook, you know, to keep your lab report sheet clean. And then we need the mass of the plastic. The notebook doesn't have to be organized. It doesn't have to be neat. You can make, you know, mistakes here, make a mess, which is fine. You just want to keep the reports clean. And make all your mistakes in your notebook. Now, notebook, this is not a proper scientific notebook. This is just quadrilled graph paper that I have. I should have bought one. But the mass of the plastic, again, is 21.98 grams. 21.98 grams. All right, so let's go on here. Now, now we can calculate just the paper, the mass of the 250 sheets of paper alone. So let's go ahead and do that here. And so if we have this is the mass of the packet, which includes the paper and the plastic. And so the mass of the paper is just going to be this minus this. So let's go ahead and take that. And so we'll have 1137.55 minus 2198. 1115.57. Grams here. All right, then we can get the mass of one sheet by doing the same type of calculation. You know, we have 250 sheets, there's a mass of 250 sheets, and then take that divided by 250, and then we're going to convert that to milligrams per sheet here. And so I'm going to leave these two calculations, actually these three calculations for you to do. Notice the unit here, you know, the units are you're going to get grams per sheet, but if they're already asking you for one sheet, then we don't need to write grams per sheet. It's just the mass of a sheet. Okay. And so you're going to have to complete these calculations yourself. All right, I haven't been watching the chat here, but I think you got it. Can you pan the camera? 50.3 microliters. Yeah. Okay. So complete those calculations for the report. All right, now, let's see, do we have to do something else with this? Yeah, we're gonna have to measure the length of thickness. Okay, so let's go ahead and measure the thickness of 250 sheets. Oops, get this panned out. Thickness of 250 sheets. And so I have an assistant here. No. Okay. Let's see. We're going to measure the thickness. Let me try to get this. So what I'm going to use is use this small ruler here. Now we're going to measure it in centimeters here. So measuring the thickness of 250 sheets is difficult because we're going to also get the plastic in there as well. So that's going to be a potential problem here. And so let's try to line this up, and I'm going to compress the sheets here. Get rid of the air. Let's see if there's a better spot here. Okay. Can you hold? Focus. Take a picture of this too. So I'm trying to line up the 0 mark over here and then measure it over here, but it's tough. And so what I'm going to do is I'm going to snap a picture of that and see. And we'll just take a look at the picture. Yeah. Maybe I lined it up. It might have, it's hard to see. So let's take a look at the picture. Okay, I didn't exactly hold it straight there. Do you see it's tilted at an angle? If it's tilted at an angle, then I'm measuring a longer length this way. So let me redo that here. Hold on. Let me put this over. Okay, I'll try it again one more time. The plastic is hard to see through that. That's a little bit better. Yeah. One of the things is it's hard to tell if I lined it up properly here because of the plastics interfering and the color of the plastic. It's not very transparent. And so it's pretty opaque there. It's hard to see through it. But we could see this edge. And so where does it look like the paper lines up to on that edge? Can you tell me? Let me measure that. Okay. Take the measurement. What do you see? Oops. Come on. Okay, so I'm just going to zoom in on this edge here. Sorry if you're getting motion sickness there. Okay, if it lines up right on the line, then what do we call it? All right, so if you take a look at this, it's 2.1, 2.2, 2.3, 2.4, 2.5. 2.6 is the next one. And so, yeah, we would have to call it 2.50 to indicate, because there's no guessing on the 2.5. You know, because 2.5 is this dark line here. And so there's no guessing. What we're guessing is, where does it lie in relation? If it's right before the line, we might say 2.49. If it's right after the line, we might say 2.51. But since it's right on the line, it's going to be 2.50. I'm measuring from the very edge of the paper right here. Oops. The very edge of the paper. There. Ignoring this plastic's going out, but it looks like the very edge of the paper lines up right there. I know the color is color is hard to see. Is it working? Am I still on, or is it not working? All right. Okay. So 2.50 is what we're going to call it. I'm going to call the thickness of 250 sheets. Let this focus again. Thickness of 250 sheets is going to be 2.50 centimeters. And so we'll record that in our notebook here. And so 2.50 centimeters. So we're going to do this width of one sheet. Oh no, here, thickness of one sheet. So we'll do thickness of one sheet next. And so if that's 250 sheets, then one sheet will just be 250 divided, 250 divided by 250. All right. So here, 250 divided by 2.5 centimeters divided by 2.5 centimeters divided by 250 sheets is going to give me 1/100 or 0.01. And so it's going to be 0.01 centimeters for one sheet. And so I could put 0.01 centimeters per sheet, or I could just leave it like this. Thickness of one sheet is equal to 0.01 centimeters. So we can put that here. But 0.01 centimeters is probably not the best. Now, centi and micro aren't related, by tens of the third, because centi is 10 to the squared, so 10 to the minus 2. So what we have to do is we have to do some conversions here to do that. You can use various conversions, but the standard conversion would be this. If I had 0.01 centimeters per sheet, then I want to convert it to, what do I want to convert it to? Micrometers per sheet up here. And so we convert it to micrometers per sheet, and I would do 1 meter is 100 centimeters. I'm just going to use the ones I'm familiar with, even if it takes more effort. And so then we're going to go to micrometers. There's a million, 1 times 10 to the 6 micrometers, a million micrometers in a meter. And so let's just take our previous number here, 0.01 divided by 100 times 1 times 10 to the 6 is 100. And so 100 micrometers per sheet. That's the thickness. And so that would complete this calculation here. Then we're going to do the length and width of one sheet to calculate the area of the sheet. So let's go ahead and measure that out. So the length and the width I'm going to have to use, I can't use that little ruler I had before. I'm going to have to use this one here. And so I'm going to take the measurement. There's some tape here, so I'll try to line up the edge here with my finger on this side, just to line it up here. Feels lined up there, and then I'll just snap a picture of this one. Let's take this measurement here. Okay. All right, let's take a look at that measurement here. Let's see. Maybe need to hold it a little bit more perpendicular. Might be a little bit of a turn there. All right, so let's see if we can see. Some of the lines are faded here, so it's kind of hard to see. It looks like this is 27 here. And so this would be 27.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 28. So this line got faded. This is the 28 line here. Looks to be. And so let's try to determine this again. This is going to be between 7.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8. So it looks like it's between 27.8 and 27.9. And so what do you measure there? 27.8 what? 27.8. 5? Yeah, that looks reasonable. Is that what? 7.85. Okay. So we could go with that if that's what. Let me see what other people got. Yeah. Okay, we'll go with that. 27.85. Okay, that was the length. And so down here, I'm going to put the length. That was the thickness. So length equals 27.85. The length of the sheet, centimeters. Okay. Now let's measure the width of this. Or here, actually, I think I can do this. I'll have the assistant helping me. So again, I'm going to try to line up this edge here with my finger, but then try to get this edge here. So I'm going to just take a picture of this edge here. Easier to measure. Again, this meter stick is pretty faded. So the markings are wearing off, but let's take a look here. This is 21 here. This is 22. So this one's 21. Actually, the bottom one's probably better. Let's go with the bottom, except the packet got screwed up. So let's go up here. So this is 21.1, 2, 3, 4, 5, 6, 7. It's hard to see. It's pretty hard to see. Let me try a different spot of this. I'm going to use the bottom of the stick here. Measure it. Let's see if that one worked better. Yeah, a little bit better. Let's take a look at this now. So here I have 22. And so this would be 21.9, 21.8, 21.7. So actually it looks like it's between 21.7 and 21.8. And so let's mark the edge of the paper there. If the edge of the paper is there, what do you estimate it is? Looks like it's 21.7, what? A little past it. And so 21.7. 2. Yeah, that sounds good. 21.72, we can go with that. And so, okay, thanks. So the width we're going to do is 21.72 centimeters. So we have the length and the width, we have the thickness of the paper. We can calculate the volume, but we aren't going to calculate the volume of the paper. Here, let's see what they're asking us to calculate. They're going to ask us to calculate the area of one sheet of paper. And so this is going to be length times width. So we could do that here. So if we have length times width, we'll get the area. Here. Let's do that. So I'm going to get 27.85 times 21.72. 604. Now, as far as sig figs go, there's a multiplication. And so we have 4 sig figs in the length, 4 sig figs in the width. And so the area should have 4 sig figs. So 604.9 sub 0. It's 902. We'll just carry 1 extra digit there. Centimeters squared would be the units. So, okay, so we have the area of one sheet. And the next calculation is mass per square centimeter of one sheet. So I want to figure out what is, if I had 1 square centimeter of paper, one sheet, how much would that weigh? And so grams per centimeter square. And so we need to know how much does 1 sheet of paper weigh total. And so we go back up here and look for the mass of a sheet of paper. Do we have that? We have the mass of 250 sheets. Here. Oops. We have the mass of 250 sheets. So now we'll have to figure out the mass of 1 sheet of paper. So let's go ahead and do that. Was that one of the calculations? That was one of the calculations up here I asked you to do. We'll go ahead and do that here. So mass of 1 sheet is going to be 1115.57. 1115.57 divided by 200. Oops, divided by 250. And so mass of 1 sheet is 4.46. Actually, how many sig figs? 250 is exact. And so we're allowed, actually, that's 4, 5, 6. We're allowed 6 sig figs. So I'm just going to use them all. 4.462. 28. That's 6 sig figs, grams. That's a mass per sheet. Okay. We can get milligrams per sheet. If this is grams, the milligrams we move it 3 places over. And so it would be 4,462.28 milligrams per sheet. We can also put it in units of grams per sheet, which we're going to do here. So that's how many grams per sheet we have, and then how many, what's the area? So what we're going to do, what I'm going to do is I'm going to do a dimensional analysis rather than algebraically here. And so what I want is I want the grams, actually, well, they wanted some grams per square centimeter, so I'll just figure that out here, like this. So 40. Next page. In the last calculation here, I have that we have 4.46228 grams per sheet. And then I want to get rid of sheet. And I can get rid of sheet by putting in the square centimeters here. And square centimeters is going to be my previous data that we calculated, 604.90 square centimeters per sheet. This is the area of the sheet. So we're going to use that as a conversion factor for this calculation here. This is going to be 604.9 sub-0 square centimeters. And so the sheets will cancel, but will give us the grams per 1 square centimeter. And so I'll take that divided by 604.9 equals. Okay, this is going to give me 7.37. I'm allowed 4 sig figs, so 7.376, that's 4, and I'll carry 1 extra, 8 here. But when I carry 1 extra, I don't round it. You know, I just drop all the other digits because that would set up a cascade of rounding, which I don't need. So this is going to be times 10 to the minus 3 grams per sheet. Not per sheet, per square centimeter of sheet. All right, but grams is not the best unit. In fact, if I were to look at this, milligrams would be the best unit, you know, because if I move the decimal 3 over 10 to the third, then this is going to just be 7.376 of 8 milligrams per sheet. Per square centimeter, sorry, per square centimeter of sheet. Just move it 3 over times 10 to the third. Now to convert this to micrograms, I move it 3 more over. And so micrograms are okay, but it would be 7,376 sub 8 micrograms, 0.8, 7,000, or about 0.8. So let's see, micrograms per square centimeter of sheet. And so let's round that to the correct number of sig figs. Rounding it to the correct number of sig figs, we get 7,377 micrograms per square centimeter. So, you know, converting from, let's say, grams to milligrams, we move the decimal 3 places over. Now, milligrams bigger. Or no, grams bigger, milligrams smaller, so it's got to be a bigger number here. Micrograms are smaller than a milligram, so this has got to be a bigger number by a factor of 3, or 3 orders of magnitude, not a factor of 3. So I would say probably milligrams is not good. I would say milligrams is probably the best. About 7 milligrams per sheet versus 7,000 micrograms per sheet. But they wanted micrograms per sheet, so we have to do what they asked for. What they asked for is micrograms per sheet, 7,000, whatever. Per square centimeter of sheet, sorry. Per square centimeter of 1 sheet. All right, that leaves the final section, section E, determination of conversion factors. What we're going to do is we're going to measure 5 lines here. We're going to measure these 5 lines here. We're going to measure these 5 lines in centimeters and in inches. Okay. So these are going to be experimental, and then we're going to calculate, a couple of things. So let's measure line 1 here in centimeters. So what I need to do is I need to line up the 0 mark here. Try to do that. My vision isn't so good, so it's hard for me to see if I'm lined up right there. So maybe what I'll do is I'll just let's take a picture of that and see if I lined it up okay. Now, so let's take a look at the 0 mark and see how I line that up. See, I'm off a little bit. Do you see that? And it depends on how you line it up. You want to buttress it, against the edge, or should you put it in the center? Well, we measure off the center, so ideally, the end of the line should be in the center of that black mark. That should be the center of the target. So, a little bit. I need a magnifying glass would help. Do it, but at least the phone's helping with the precision. Now, if I didn't have this phone and if I couldn't blow it up, then, obviously there's going to be some error associated with lining these things up. Let's take another picture of that and see. It did this time. See if I got it better lined up. Okay, this is better here, but oops, really can't see. This is better here, except I'm still, not even the edge is quite properly lined up there. And not only that, if you look at the surface, it's not completely flat on the edge there. Do I go to that, the end of the rounded part there? Can I even see that with my naked eye? Probably not very well. So if you're just doing this with naked eye, that's what we're doing, but we're trying to get some decent precision on this here. So let's try that again. And take another shot at this and see if I got it better lined up this time. All right, there, it's not quite right in the center, but I'm just gonna, rather than taking 1 hour to get it perfect, I'm gonna go with it. It's gonna lead to a little bit of error, but that's okay. Now, normally when people do take length measurements, they measure it edge to edge, So they measure the edge there, but when they do the length on this side, on the opposite side, they don't measure edge to edge, they measure it in the center, where does the center line up? So we have to be careful. So that little bit of difference is going to lead to a little bit of error, and so we're going to expect it not to be perfect, But we'll just go with it. Okay, let's measure the other edge here. Just take a picture of the other edge here. So, okay, I see 8. It's between 8.3 and 8.4. And so what would you call that? .36. What else do we have? Yeah, it depends if you go to the edge of the blurry line there, 8.36. I could go with that. What else did people say here? Let me move this a little over. 8.35. I could go with 8.35. I could go with 8.36. There's going to be a little bit of uncertainty in that. 6. All right. Any others for 5? Yeah, it depends on where you take it because it's hard to see where the exact end of that line is because it's kind of fades out. You know, there's a little ghost image of the end there. So we'll just go with 6, I guess. 2 people. It's 6, and so line 1 is 8.36 centimeters. So let's go with that. I'll write that here. So 8.36 centimeters. Okay. Now, what we're going to do is we're going to measure the exact same line, but now in inches. And so here, I have my assistant. Let's see if I can line it up here with the edge. Best I can. Lines are pretty thin, so you're doing it at home. It's not so easy. Okay, let's take a look. All right, this is kind of, you know, what I was talking about. Maybe the edge of the line with the center of the 0 mark there. We'll just go with that. You know, but normally what people do is they line it up edge to edge. So maybe that's close enough to edge. But if it's edge to edge, then it's going to lead to a little bit of error because when you measure the opposite side, it's usually, you know, if it lands on the center of the line, that's what you'd call it, not on the edge. Let's see what this one is. Yeah. All right, now this is going to be a bit trickier to do here because we're using the inch scale. And so this is measuring in 16ths. So there's 16, so this is 1/16, 2/16, 3/16, 4/16, all the way to 16/16. And so we're measuring in 16ths. And so what we're going to do is we're going to count it out here. 1, 2, 3, 4. So we're between 4/16 and 5/16. And so what would you call that? Between 4/16 and 5/16. What do you call that measurement there? Okay, 4.9. Do others agree? Okay, that sounds about right. 4.9 looks good. So what we'll do is, okay, so this next measurement is going to be 3 and 4.9/16. And so that's what we're going to write here. It's going to be 3 and 4.9/16 inches. Now, those are our two measurements here. We're measuring in centimeters and we're going to measure it in inches. But the inches, we also want it in decimal notation. So we're going to convert this to decimal notation. The way we convert it to decimal notation is we just take 4.9 divided by 16. 4.9 divided by 16 equals. And then I'm going to add that to 3. And so I'm converting this fraction into decimal, which is this 0.30625 plus 3. And so what this is going to equal in terms of decimal notation is it's going to be 3.30. Now, how many sig figs am I allowed? Well, this is an addition. We're going to take 3 as exact. There's no uncertainty there. You know, for sure, it was past 3. And so, for sure, it was past 3. And so that's exact. So that's infinite sig figs. And so when we're doing the addition, I should have probably done it like this. It's going to be 3, which is exact, plus 0.306. We're only allowed 2 sig figs, so we'll just carry it there. So it's 3.306. Now we're allowed 2 sig figs for this, which means 2 decimal places here. So we're actually allowed 3 sig figs in our final answer because we had 2 decimal places here. And so that's going to be sub 6 inches, or 3.31 inches. Yeah. But I'm not going to round it just yet, you know, because we're going to do one more calculation here. The one more calculation we're going to do is this one. We're going to figure out the centimeters to inch ratio. And so to figure out the centimeters to inch ratio, I have 8.36 centimeters divided by, I'm going to use this one here, 3.306 inches. That way I have less round off error. Actually, I'm just going to use the whole value of my calculator to avoid round off error. I'm going to invert that times 8.36. So this gives me 2.528 centimeters per inch, which rounded to the correct number of sig figs is going to give me 2.53 centimeters per inch. Now, I'm off a little bit because what is it supposed to be? It's supposed to be 2.54 centimeters per inch. And so how far off am I? Well, I could just do a quick calculation here. So this is it. This is my experimental minus the theoretical is 2.54. Okay, equals that, divided by the theoretical, 2.54 times 100%. And so this is minus 0.45% error. You know, when I look at this number is a minus 0.45% error. And so we're off a little bit, but you know, it's hard to get it right on. You know, and the line wasn't perfect either, so it's hard to measure. But whatever we do, we have to try to be consistent. And so let's take a look at some of these other measurements. Now, to save time, I'm not going to be as precise. I'm going to accept a little bit of error. And so I'm going to just line it up on the left side as best I can here. You know, we have to think about time. You know, we could spend hours and hours lining it up perfectly, but to get better results, but do we have that time? And so I'm going to say we don't have that time because we've got to get through 2 more experiments today. And so what I'm going to do is I'm just going to line it up on the left side best I can. So that was an eyeball. So we'll just go with it. But just as a check, let me just take a photo of that and then see, you know, for reference. So that looks okay. Oops, I don't know if you can see that. That looks okay on the left. But even if it was off, grossly off, then I'd probably readjust it, but it wasn't, so we'll just go with that. And then let's read this one here. So this one is between 11 and 12. So what would you call that? Oops, what would you call that? You know, this is why I'm talking about center of line. You know, that line is thick. And so this 11.3 line, that line is thick. And so I wouldn't call that 11.30 because I'd call 11.30 right in dead center of that line. You know, what would you call this though? Maybe you call it 11.30, maybe it's close enough, but you know, it is kind of on the line. I wouldn't, we're not allowed to estimate that far down. 11.301, we can't, you know. So what we have to do here is this. We divide it into 10 imaginary lines, basically. And so three zeros right dead center. And then right in the middle is 3, 5. And so dead in the middle is 3, 5. So what we have to do is we have to go from the dead center here to the middle here and call that 5 lines. We have to draw 5 lines in. So 3, 3, 1, 3, 2, 3, 3, 3, 4, 3, 5. And so what would you call it? Anthony. Actually, Anthony's probably on, but you just you're just being a little over. Yeah, 3, 1. That's it. That's what we need. And so I'd probably call that like an 11, 3, 1. What do you guys agree? Would you like to go to 3, 2? Because there's a little ghost edge here. You probably could take it out to 3, 2, or maybe even 3, 3. You know, depending on that, you know, where you call the edge. The edge of the line is not so clear. Okay, so we're going to go with 3, 1. And so this is going to be line 2. 1131.
Can't see.
Centimeters. Oh, sorry. Okay, there we go. 1131 centimeters length. Okay, now we're going to do the same thing for the inches here. So let's go ahead on. I'll try to line it up the best I can, the inches. So let's see how I did on this side here. Quick check. So it's off a little bit, you know. Look, it looks like, yeah, I'm off a little bit. Well, actually, this one I'll just tap a little bit over this way. Just tap it over a little bit over there. See if that is a little bit better. Okay, maybe a little bit better, but it's still edge to edge. And I should get the edge of the line in the center of the 0 mark, but I'm not going to waste any more time with that because we got a lot of other things to do. So that's going to be good enough. Okay, let's mark the left, that was the left edge. Let's mark the right edge here. See if we can get that in inches. All right, so we're at 4, and let's count the 16ths here. Okay, so it's 4 and 1/16, 2, 3, 4, 5, 6, 7. So it's between 7 and 8. I'm a little high here. So what do you measure this? It's 7 point what? 7.3? Okay, do others agree? Yeah, all right, let's go with that. 7.3 sounds good. And so that was 4 and 7.3/16 inches. All right, and so let's convert 7.3 into decimal form. So this is going to be 7.3 divided by 16 is 0.45 plus 4. 4.45. Now this is 2, so this is going to be 4 plus 0.45, that's 2 sig figs, so we'll carry 1 extra, sub 6. And so this is going to be 4.45 sub 6 inches in decimal form. Okay, now let's go ahead and calculate our centimeters per inch here. And so it's going to be 11.31 centimeters. This is a calculation. per 4.45 inches. So what does that come out to? So I'll just invert what I have in the calculator, times 11.31. Okay, this comes out to 2.538 centimeters per inch. And I'm going to go with this as my experimental here without rounding. And so this is my experimental. I'll just use all the digits in the calculator. Minus 2.54. That's the theoretical. Divided by theoretical, 2.54 times 100%. And this one, we're off by 0.078% error. So this is a bit better. This one's going to round to 2.54. If I rounded it, then obviously there's 0% error, but that's because I rounded it here. When we do the average, I'm not going to use the rounded. I'm going to just carry one extra digit here. All right, that's line 2. Let's do the line 3 next here. So normally we do, you know, if we're trying to do this experiment, normally we do 3 measurements. Most people will do 3 measurements to get some statistically meaningful result. But here we're doing 5. Okay, so let me check the left edge here. See if it's close enough. Okay, that looks good. Close enough. Left edge. Now let's get the right edge here.
Professor?
Yes?
It's break time.
Okay, it's break time. Wow, I need to pick up the pace here, but let me just take a picture of the right edge here. And then we'll measure it after. All right, let's take a break for 15, and then we'll start up again after the break. All right. So I'm going to pause the recording. Okay, so do you guys have a ruler at home? In other words, do you want to finish this at home? No? Okay. Then we'll just finish it here. All right, so I recorded that last one, and so let's take a look at that last measurement here. This is line 3 in centimeters. And so what do you call that? .25? 9.24? All right, 9.25 would be right in the center, but you know, it's hard to tell because the line, you know, the edge of the line is not so clearly defined. Yeah, it could be 9.24, 9.25, 9.26, all those are acceptable because it depends on kind of where the ghost of the line ends. And so, just one second. Okay, so since there is, I probably would have gone, because just based on the density of the line, I probably would have gone with a 9.24, you know. But it could be 9.26 if you take, you know, the very edge of that, you know. But it looks like we got 9.24s. Yeah, let's just, maybe we'll go with the densest part of that. Maybe we'll just go with a 9.24 there, or 9.25. Let's see if what the error comes. We'll just keep that as a little bit uncertain. The line 3 was, you know, 9.24 centimeters to about 9.26 centimeters. So we'll keep that there. Exactly. Let's do this in inches, line 3. So try to mark this here. So let's take a look at the left edge. You know, I wish they made the lines with a thicker point size. I don't know why they made it so thin. A little thicker would make it maybe a little easier to measure. And with a little higher DPI on the printer would be better as well. But anyway, this is what we got, so we just got to deal with what we got. And so I'm off a little bit. I need to tap it in a little bit more. Let's try that there and see. Just moving this a little bit. Yeah. Okay, that's kind of edge to edge. I mean, that's kind of what you'd measure, although it should be the edge of the line to the center of the 0 mark. But I'm not going to fiddle around with it too much more because of time constraints. Okay, let's look at this side here. All right, when we look at this side, okay, we'll just go with that. It's going to be 3. Okay, the center would be 8/16, so this would be 9/16. It would be 10. It's between 10 and 11/16. So what would you call that? 10 point what? $10.3, okay. Anybody else? Okay, that looks good. We'll go with 10.3. And so that would be 3 and 10.3. 3 and 10.3. Yes?
Can't see what you're writing.
Can't see. All right, sorry. 10.3/16 of an inch. Sorry. There we go. Okay, so I'm going to convert that from fractional form to decimal form. So let's go ahead and do that. And so we're going to go 10.3 divided by 16. And it's going to give me 0.64. I'm allowed two sig figs, so this is going to be 3, which we're going to take as exact, plus 0.64 sub 3. It's exact. It's greater than exactly 3. There's no uncertainty there. So this is going to be 3.64 sub 3. When you make a mistake, you just cross it out, you know, with a couple lines. You still want to leave it legible. So you still want to see what the mistake was. You don't want to completely block it out with ink. And you're supposed to record in ink. You're not supposed to record in pencil because pencil eventually will fade. So that's a problem. All right, and so we're going to go centimeters per inch, and that's going to be 9.24. We're going to go on the low side here and then see 9.24 centimeters per 3.64 sub 3 inches. So I have that inches in my calculator still, so plus 3. And so what I'm going to do is I'm going to invert that. And so I'm carrying actually more digits here than I have. And that's good because that helps minimize rounding error, times 9.24. Try that again, 9.24. Okay, so this gives me 2.535 centimeters per inch. Now let's go to the other extreme. The other extreme we had was 9.26 centimeters per the same 3.64 0.43 inches. And so I'm going to do that calculation, but I'm not going to carry it in my calculator here. It's just going to be straight 9.26 divided by 3.643. Okay, and this gives us a 2.541 centimeters per inch. Actually, this one has a smaller percent error. So 9.26 is much closer. You know, let's calculate the percent errors between both of these. So if I look at the 9.6, it's 2.54, which is my experimental, minus 2.54, which is theoretical, equals divided by 2.54, the theoretical, times 100%. And so this one is only a 0.073% error here. How about this one up here? So this one is a 2.535 minus a 2.54 equals divided by 2.54 times 100%. And this one comes out to a 0.196 or 0.20% error. So this is about a 0.20% error. This is a 0.073% error. So this one turned out to be closer. So maybe that's right. This is closer to 9.26, was more consistent with the way we measured it. Okay. Now, when scientists are always pressed for time, and always being pressed for time means this. Obviously, we'd like to do this, you know, 1,000 times, or we'd like to do this 1,000,000 times. But each time we measure a line takes time, and you know, it's kind of tedious. And so what's best? What's the best number of measurements to take, you know, the best number of measurements to take to come up with a statistically meaningful answer? And so when we're thinking about measurements, one measurement, you know, statistically, you're exposing yourself to a lot of risk in terms of random error. You know, if you only take one measurement, you know, that measurement could be off quite a bit. And if you take 1,000,000 measurements, that's better. If you take an infinite number of measurements, that's the greatest, because if we kept doing this, and we took an infinite number of measurements, eventually we're going to get an average that's right on. It's going to be 2.54 centimeters per inch. But we don't have time to take an infinite number of measurements. And so based on statistics, it turns out that the best return, you know, minimizing that error versus the number of measurements comes at 3. So for example, if you do one measurement, then scientists calculate something called the 95% confidence limit. And so if you do one measurement, then statistically, there's a huge range of uncertainty. If you do 2 measurements, then that's going to narrow the range significantly. If you do 3 measurements, it's better. If you do 4 measurements, it's better. But you know, the better, it's just a little bit better. If you do 5 measurements, it's a little bit better. So pretty soon, the difference between taking 20 measurements and 30 measurements statistically is very small. Yeah, 30 is better, but just by a tiny bit. Is it worth doing 10 more measurements of these lines to get that little bit of extra? No. And so the best return on investment, time investment, is with 3 measurements. Yeah, 5 measurements is better, but it's not a huge, we don't expect a huge improvement in our uncertainty with 5 measurements versus 3 measurements. So with that being the case, I'm going to stop because it's standard. In science, it's standard because it's standard when the measurements take a lot of time. If you could do measurements rapidly, then you could take 1,000. Like for example, when I was using instruments, I take 10,000 measurements. It's no problem because each measurement, you could take 10,000 measurements in like 10 seconds, you know, something like that. And so this is very time consuming. So here I'm going to think now, statistically, I wouldn't have stopped at 1. I wouldn't have stopped at 2, but now I'm at 3. 3 is okay, you know, 3. If I go to 4, then it's a little bit better, but it's not worth the time. So we're going to stop at 3, and then we're going to do our calculation here. And so this is what I'm going to ask you to do for line 4. For line 4, just cross it out. And then for line 5, cross it out. We're not going to measure those. So we're going to base our centimeters per inch on 3 measurements. Okay, so we're going to calculate the average value. of centimeters per inch for those three measurements. And so let's take a look at the previous. Values that we got here. Okay, so I'm going to go with more digits. I'm not going to use the rounded version here. I'm going to just carry one extra to try to help minimize round-off error. So the first one was 2.528. So I'll put that in, 2.528. Okay, plus the second one. The second one is 2.538. Plus 2.538. And then the third one. The third one was 2.535 or 2.541. Well, since we took both measurements, let's just go with this one here. Well, actually, we'll average both of these in. You know, we took two measurements of the same thing. So we're going to do an average of four. Four measurements is better. So we'll go 2.535, so plus 2.535, and then I'm going to add this one here, plus 2.541, because we repeated that measurement, and so that gave us a total of four measurements. And we'll add those up and divide it by 4 to get the average. And so the average of four measurements is 2.535, 2.5355. And so we're just going to round it to the correct number of sig figs that we should have. This is centimeters per inch. Actually, what is the percent error in our average? So this is our experimental minus the theoretical 2.54 equals divided by the theoretical 2.54 times 100%. And this is going to give us a minus 0.177% error. Actually, that's one of the calculations they're asking for here. And so the average, we're going to carry the average with more digits here. Because if I were to round the average, let's say if I were to round this, you know, this is 2.54 centimeters per inch, which is the correct number of sig figs that were allowed for this, which would be a 0% error, but it really isn't a 0% error, you know. And so let's use this value here for the average. Now, the percent error, we probably should show the calculation here for the percent error here. The percent error is equal to the experimental value minus the theoretical value divided by the theoretical value times 100%. And so the experimental value 2.5355 minus theoretical is 2.54. We know it's exactly 2.54. Because there's a percent error. And so we based it on four measurements. Now, what we need to do is, you know, it's 2.54. That's our answer. It's 2.54. In science, we do plus or minus. The plus or minus here is what's called the 95% confidence interval. And the 95% confidence interval is going to depend on two things. Depends on two things. The two things it depends on are the number of measurements the more measurements we take, the greater the number, the narrower the range, you know, the smaller the range. So the greater the number, the smaller the range. That means it tightens the uncertainty. A large range means, you know, a large range means a large range of values in centimeters per inch, which means that it's uncertain, you know, so the narrower the range, the better. And so here's the trade-off, you know, it's not linear. It's not like two measurements is twice as great, you know, it's non-linear. And so pretty soon the payoff becomes very small. And so here, let's say if you take one measurement, you get a huge range.
Professor?
Yes.
Can you repeat what all that says? Because we can't really read it.
Okay. this has 95% confidence interval. You know, depends on two things. Actually, it depends on the number of measurements. Let's see. The more measurements, the smaller the range. So if you take one measurement, you have large uncertainty, the range of uncertainty. Maybe I should write bigger. If you take two measurements, that range drops dramatically. If you take three measurements, it drops dramatically more. With four measurements, it drops, but not as dramatically. The biggest improvement is right at the beginning. And then as you go on, it gets a little bit better, you know? And so statistically, taking three measurements is best, you know? Four is a little bit better, but not a huge improvement. And so this is why we take three. That comes from the statistics of this. The second thing that it depends on is the scatter. You know, when we look at the individual measurements, if the individual measurements are all close together, that is, they're all with pretty good precision, they're close together, then the range is small. But if they're all over the place, that is, if we have measurements that are close in agreement, and so we'll call this measurement agreement. All the measurements should be the same. You know, we should get about 2.54 centimeters per minute. And so if the measurement agreement is good, then the uncertainty is small. The range of uncertainty is small. If it's bad, then we're going to have a large uncertainty. So if we have good, like say our first one was 2.5355, but our second one was 2.08, and our third one was 4.63. Well, that's going to mean, well, what the heck, you know, that's going to have a huge range, you know. But if our first one was 2.535, our second one was 2.538, and our next one was 2.541, then we're going to expect that. And so typically when we report an average, we report the 95% confidence interval, but this is not in this class. This will be in Chem 1A-B. You should be able to do that kind of stuff. All right, are there any questions about this lab? Okay, did you guys catch this, what this says? Yes? All right, good. Okay, we're done with this lab. Let's move on to the next lab. Okay, the next lab we're going to be doing is the Charles Law lab. So let's find Charles Law lab. Here. What? I wrote on this one already, but it's all right. All right, so this is experiment 7, Charles Law. This is the data we're collecting here. So I think it's 7-3. Did I screw that up? It's 8A, Charles Law alternate. We're not doing the alternate. Did I lose the pages? Let me look for my pages here. 1 second. Well, I guess I did lose the pages for this, the procedure. That's all right. Try to figure it out nonetheless. Actually, I have it here. I'm going to share the screen. Okay, I need to minimize or move this. It is experiment 3. Sorry, my lab manual's old, and I wasn't given the latest one, but it's all right. This is the same experiment. Okay, let's take a look at the apparatus here. The apparatus that we're going to need is a Florence flask, 500 milliliter Florence flask, and we have to find the proper rubber tubing. And so let's go, I'm going to go look, and we need a 1500 milliliter beaker with a, let's see, with tap water, half fill. Okay, so I'm gonna go get some equipment here. So let's go find our 500 milliliter Florence flask. Actually, I have one here. So this is our 500 milliliter Florence flask. The Florence flask is gonna have a round shape to it, but it's gonna have a flat bottom. We have round bottom flasks as well that have a round bottom on it. Round bottoms obviously aren't gonna stand up on a counter. So we have special holders for round bottom flasks, but this is it. Okay, now I have to find a stopper with a hole and a glass tube that fits this. And so let's grab that. Can you check those? Okay, so here, see if that fits. Okay, what we want is we want a good seal there. If you can see that here. It's got to be a good seal. Can you twist it off? Twist it off? Yeah, like that. Okay, let's take a look at this. Now this is a stopper, rubber stopper. Can you guys see the video? You need me to switch back to it, or is that adequate on a small screen? Okay. All right. So we have a Florence flask that's stoppered here, and the stopper has a hole, and there's a piece of glass in here, a glass tube, and the glass tube is open to air. So this is open to air here, like that. You can't, okay, is it okay? Can you guys see that, or do you need me to go full screen?
Sorry, I don't know what I was typing. Sorry about that.
Oh, okay, all right, just want to make sure. Okay, now, all right, that's good. Now we need a 1500 milliliter beaker. I accidentally grabbed a 1000 milliliter beaker. I have to grab a 1500 milliliter beaker. So let me go grab that from the stock room. Give me 1 minute. Is that 15 or is that Okay. So right now we got the Florence flask with the stopper, and then we're gonna half fill a 1,500 milliliter beaker with tap water. Now this beaker is quite dirty. Wait. Let me show you. There's a lot of hard water deposits, like calcium carbonate. We can clean these off with acids, but this is the problem. If we use DI water here, then we wouldn't get these hard water deposits. So we're using tap water here. And so this hasn't been cleaned, but I'm gonna fill this up with tap water here. Go ahead and fill it up here. I have my assistant here helping. My assistant doesn't want to be on camera, so do that. Okay, that's good. Now come over here. Oh. All right, so we have the beaker here. Okay, now we're going to heat the air in the flask, measuring the higher temperature. Okay, place the stoppered flask in the 1,500 milliliter beaker of warm water, leaving about 2 centimeters between the bottom of the flask and the top and the bottom of the beaker. Secure the flask in position. Okay, so we might have to add a little bit more water. Okay, and so what we're going to do is we've got to figure out how we're going to do this, because we're going to need to boil the water. And so we're going to have to set up our apparatus. So in order to boil the water, we're going to use a burner, Bunsen burner, to do this. Oops. That wasn't good, but fortunately it didn't break. So, so I have my ring stand here. Let me go full screen for a minute. Let's see if I can stop. Okay, I think this is full screen now. Oops. Can you guys see it? And switch back. Trying to make this bigger so I can see it. Stop the share here. Okay, now I can see it. Okay. So we have, this is the ring stand here. All right, so this is the ring stand, and this is what we're going to use with the burner. So we're going to put the burner here, and then I want to get an idea of where, actually, of where that's going to lie. Let me move this here. Okay. All right, so I'm going to light the burner here. So light the match first. Hold it back a little bit. Thanks. You don't have to zoom in on this. And then turn on the gas over here. I'll turn it on gently. Just to try to not blow it out. Okay, again, a hot match we want to set aside. Let's see how stable this is. That's okay. Okay, I'm going to heat up water, so I want as big of a flame as I can get here. And so I'm going to turn up the gas a little bit, but again, I don't want the gas too big and have no structure in the flame. I need a nice cone in that flame. So let's try to increase the air here to get some cone. But what I'm going to have to do is I'm going to have to compromise on this to turn down the gas a little bit so I can get a cone. And let's see if you can see the cone. You see the cone there? Oops. That was about the max. I just about screwed off the barrel. Let me see if you can see the cone. Can you see the background? Black background, that'd be easier. Okay, so we want a cone there. Let me see if I can get the flame a little bit bigger and still maintain the cone. So I'll turn on the gas a little bit and then unscrew this, but I'm at the end. I can't get any more air in there. This is the maximum amount of air, get the maximum amount of gas to get it, the flame there. And then I'm gonna size up where the cone is. You know, the tip of the cone is gonna be the hottest part. So it's about right here, right there. And so that's where I want to mount the beaker. I want the beaker to sit right at the tip of the cone here. And so if the tip of the cone is, see, I know it's hard to see, but the tip of the cone is about right here. So I need the beaker to sit about right there on this. And so I'll just make a little mental note. It's right here. Okay. And so that's where I want it to sit. And so I'm just over there. So I'm going to go back and I'm going to get what's called a ring. The rings are located in the box back here. We have two different sizes of rings. The big ring and the small ring. We use the big ring. And then I'm going to use that little wire knob to support the beaker. This is going to be kind of dangerous because the beaker can probably easily tip over. And so what I'm going to do is I'm going to put this on here like this. And I got to be careful. Obviously, I don't want to burn myself here. But I'm going to get it to about the right height, which is about here. And so I'm just screwing this little wing nut or wing screw here. I'm just going to screw that on there. Height. And then I'm just going to rotate this to make sure that the tip of the cone is hitting the bottom of this. Just hold it in one place back there. And then we'll put this here, like that. And so now the tip of the cone should be hitting the bottom of the gauze there. Okay, then I'm gonna make sure this is tight, and then I'm gonna put this on here. Unfortunately, we don't have something to clamp this on here like that. But as an alternative to that, we're going to do this. We're going to put this in here. And what we want to do is we're going to push it in and submerge it. Right now it's buoyant because it's just filled with air. And so it's buoyant. So I'm going to force this down. But I don't want it to rest on the bottom because the bottom of the beaker can get hot. And so I got to make sure it rests down there. And I'm going to add just a little bit more water to this. This was the DI water. Sorry. They're asking us not to use DI water because it's expensive compared to tap water. Okay. So I'll put this on here, and obviously this is dangerous. I mean, that's a lot of water. It could get knocked off quite easily. But what we will do here is, back up just a little bit, thanks. Is this. This is a utility clamp here. And the utility clamp you can adjust angle. And so this is a lock nut here. And so if I loosen the lock nut, I can adjust the angle of this. You know, actually this one is kind of corroded. I'm just going to make it horizontal like that. And then we can lock it back here. And so what I'm going to do is I'm going to lock this on the neck of the flask at the very top, just by twisting this and then tightening it here. That. And then I'm going to place this up here. And then I'm going to submerge the flask, but I don't want the bottom of the flask to touch the bottom of the beaker because the bottom of the beaker is going to be a little bit hotter than the water. I just want this to be floating in the water. So just push it down. Well, I can't actually. That's the max I can submerge this. And so because of this part here, move it around a little bit so you can see. Up. Okay. Okay, so now I've locked it in place here. and so it's heating. Now, boiling water does take time, so normally we set up the boiling water bath right off. Okay. All right, thank you. Okay. All right. So that's going there. Take a look at what we're supposed to do next. All right, secure the flask in position with the utility clamp, which is here. Heat the water to boiling and boil gently for 10 minutes. The flask should be surrounded by water as much as possible. Record the temperature of the boiling water with your thermometer. We're going to let this go. Now, boiling water does take time. Let me try to increase the gas here a little bit. I still got a cone there, so get that going. I could add a little bit more water here, submerge it a little bit more. But I want to be careful not to maybe splash out. Just add a little bit more water. Like that. All right, while that is going, since it's going to take some time to boil the water, we can do some other stuff in the meantime. And so what is the other stuff that we're going to do? So the numbering of the labs, we're going to do what I had as experiment 6, sorry, on my book, and I guess the new book. I don't know why they didn't give us the new book, fortunately. Oh, here's my procedure for experiment 7. The common chemical reactions, which I had as experiment 6, but let's take a look at what it is in your book. I ended up buying that, but I gave my copy away. Okay, so that was experiment 3, Charles' law. Experiment 4, percent water and an unknown hydrated salt. We're not doing that one. Skip that. Experiment 5, conductivity. We're not doing that one. Well, that's a good one. We might end up doing it. We're going on to experiment 6 here. Let's see. And so what do we have going on with experiment 6? So we'll keep an eye on this as it goes along. We're going to take a look at this now. For experiment 6, we're going to try to make some predictions and then do the reactions themselves. And so let's take a look at the predictions that we're going to make. And so first, let's take a look at the reactions. So here are some terms that we're going to use as abbreviations for our observations. It's not experiment 7, sorry. It is experiment, is it experiment? Maybe it is experiment 7. Let me see. It is, sorry. Yeah, the numbering, no, it's experiment 6. Experiment 6. They changed the name from my version. And the number. Observation of double replacement. Shoot, that's not right either. Let me check 7. Oh, okay, we are doing experiment 7. Common chemical reactions. Sorry. So on the syllabus, I had my experiment 6 is your experiment 7. So yeah, I apologize for the mix-up. I just didn't, when I made the syllabus, we're doing all of these. It's just the timing. And so we're going to do this one here. Common chemical reactions, experiment 7. Eventually we'll do all of them. So let's go back to experiment 6. We're going to look at some of the common abbreviations that we can use here. The common abbreviations that we're going to use are PBT for precipitate. Clear is usually be abbreviated with the C, C for clear. I'm off one screen here, so let me take a little bit. No, we're just looking at 7 because we're going to use some of the jargon from experiment 6, but we're going to be doing 7. We're looking at 6 because PPT, let me, well, let me show you what I mean. This is assuming here that we do 6 before 7, but we're going to do 7 before 6. So we're just going to use these terms from experiment 6 for experiment 7. We're going to do experiment 7 first, not experiment 6. Experiment 7 is going to expose us to more variety of reactions initially. We're doing, well, just follow along. Just don't worry about which one we're doing. You're just going to collect observations. It doesn't matter the number, So just follow along. Just follow along because oftentimes things change in lab. And so, ultimately it's your observations that remain. And so if you can just, regardless of what number it is, if you could just look at the terms that we're going to use, the glossary of terms here, regardless if it's experiment 6 or 7, it doesn't matter. We have precipitate. These are the definitions. We already talked about precipitate, talked about clear, colored, colorless, steam, effervescence. These are the common abbreviations we use. So PBT for precipitate, C for clear, EFF for effervescence, SOLN for solution. So clear colorless solution would be CCS. A clear colorless gas would be a CCG. A clear colorless liquid would be a CCL. The colors that we have, I usually use three letter abbreviations for colors. But, these are some standard ones here. All right, now let's take a look at some of the reactions that we're going to be looking at. So these should correlate with your lab manual. So now flip over to experiment 7. And we're going to look at some of the reactions here. All right, so the first reaction here is going to be they're calling it a combination, but we're going to analyze it a little bit differently. It says, hold a short piece of magnesium ribbon at one end with crucible tongs and ignite the other end. And so in other words, we're just going to burn some magnesium. That's going to be the first experiment. Okay. So we're multitasking here. So let's take a look at what's happening with our current experiment, Charles' law here. So I see bubbles forming. Do you see the bubbles here? Yeah. Let me stop the share. So do you see the bubbles forming here? Yeah, okay. Is it boiling? Let me ask you. Is the water boiling? The water is not, what are the bubbles then? If the bubbles aren't boiling, what are the bubbles? Yeah, I guess it's simmering. You know what the bubbles are? The bubbles are dissolved air. And so those aren't bubbles of steam, those are bubbles of air, because what happens is, you know, air is not very soluble in water, but a little bit of air dissolves in here. And that little bit of air, you know, as the temperature goes up, the solubility of air goes down. And so as the temperature increases, the bubbles of air kind of precipitate out of the solution. And so it's not quite boiling. You know, let's measure the temperature. So let me go get a thermometer. When you measure the temperature, you don't want it to touch the glass, you know. And then there could be thermal gradients. That is, the bottom of this could be hotter than the top, you know. So that's why we have stirrers. And stirrers are just to try to make sure that the temperature remains constant. But let's go towards the bottom. Let's see what the temperature is around the bottom. So when I look at the temperature here, it's a little over 80 degrees C. Not quite focusing, is it? Hard to see, but a little over 80 degrees C. So, you know, that's all these bubbles here are just air that's coming out of the water. I'm going to knock those bubbles off. Okay, so we'll wait until this gets to a nice boil. I'll leave the thermometer out now. Okay, so let's go back. We're going to take a look at this one. And so here, let me flip this around so you can see. I'm going to write this on the board. Is that new? Okay, so let's go ahead and right, so we have magnesium. Okay, it's magnesium metal. If it's magnesium metal, do we write 2+ or leave it? So should I write a 2+ here or leave it as is? 2+, yes or no? So if it's magnesium metal, should I write Mg2+? Because we know the charge on magnesium. And so Adriana, you say no. Actually, this is not magnesium metal here. This would be magnesium ion. If I'm doing magnesium metal, it's just the metal itself, Mg, and it's a solid. So we're taking magnesium solid, and then we're going to burn it. When we burn it, well, magnesium is the fuel, the reducer. And so the oxidizer, when we burn this, is going to be O2 gas. And so tell me what we form. When magnesium is burned in air, what do we form? What is the formula? Yeah, MgO. Right. Now there's two ways that we can balance it. MgO is a solid. Most metal oxides are solid. In fact, all of them are going to be solids. And one way to balance this is if we go 1/2 O2, and then it will be balanced. Or the other way of balancing it is just to double everything. So we go with 2 magnesium solids plus an O2 gas gives us 2 MgO solids. So that's what you can have here. So we're going to do this reaction next. All right. Well, the magnesium is missing. What we're going to do is we're going to let's look at the reactions first on paper, and then we'll do them. I have to go find the magnesium. It disappeared somewhere. But let's go back to our reaction, or not our reaction, but our boiling water here. Now this looks like it's boiling here. You see the bubbles of steam are being produced at the bottom of the test tube. You know that? Thanks. My assistant here. I'm going to hold this. Oops. I had this burner set up for max air, and I knew I unscrewed it all the way out, you know, to get the biggest flame possible. But I unscrewed it out a little bit too much. And so I shut off the gas there, and the barrel just unscrewed by itself there. And let me redo the flame here. Okay. Let's see what the temperature is measuring. So again, I'm going to suspend it. I don't want it to touch, you know, any glass. If it touches the glass could be a little hotter than the water itself because of thermal conductivity issues. It's not really a full boil yet, and so let's wait. Now it's boiling, but do you see? Look how big those bubbles are. Those bubbles are big. Did you see that bubble? It's quite big. Big bubbles cause, you know, turbulence, and big bubbles can cause splattering to occur. And so oftentimes we don't like big bubbles to form. So let me do something here. All right, to prevent these big bubbles from forming, we use these. These are called boiling chips or tamer tabs. Tamer tabs is some kind of, but it's just taming boiling action of boiling chips. And so if I look at what is a boiling chip? A boiling chip these are quartz crystals here. And so white quartz is pretty unreactive, you know, it's like glass. And so what we'll do is we're going to just put a couple of quartz chips in there or more. We could reuse these as well. So I put in about 4 chips in there. Let's put in some more. What the chips do is they provide surfaces for bubbles to nucleate. And what that's going to do, although it hasn't done it quite yet, is going to make smaller bubbles. And if we get smaller bubbles, then we aren't going to get as much turbulence. These are not working that great. I mean, the chips are working. We're getting a lot of bubbles forming off the chips here. But we're still getting some big bubbles forming there. I just got to knock some of those chips in the center of the beaker. That would be better. The center of the beaker is getting hot because that's where the burner's pointed. Center of the bottom of the beaker. But now we're getting a lot more. You can see on the side here, we're getting a lot more smaller bubbles form here. All right, let's take a look at the temperature here. This is a pretty good, it's getting there. It's a pretty good boil. So it says to boil it for about 10 minutes. And we boil it for 10 minutes. By 10 minutes, all this should be thermally equilibrated. Everything should be well thermally equilibrated. So let's mark the time here. I got 1:50 for the time. So we'll go until about 2 o'clock. When is break time? It's about break time now, isn't it? Yeah. So let's go ahead. Let's take a little bit of an extended break. I'm going to let this boil for even longer. So rather than our 15-minute break, let's take a 20-minute break. I have to look for a couple of things and I have to grab some stuff. So a 20-minute break at least, or 20-minute break. We'll just go with that. Okay. So I'll see you guys back in 20 minutes. I'm going to pause the recording. Or I'm going to stop it. I'll break it up into chunks.